Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will continue with the topic discussed in the last lectures. Let me write the topic. Our topic is application of statistical method to gases. We continue it. We use this color. Under this heading, today we are going to discuss our subtopic, the three distributions So let us start. In the last lecture, we discussed the three cases of counting methods. One was the Boltzmann-Einstein statistics. That is, we found the expression for the number of microstates pertaining to a valid distribution for Bose-Einstein case, that is for Bose gas. Then we did the same for the Fermi-Dirac distribution, that is Fermi-Dirac statistics. And then we talked about the third variety, third type, that is a dilute gas. And we showed that in the dilute gas situation, Fermi-Dirac statistics and Bose-Einstein statistics approach the same limit, and that limit is called Maxwell-Boltzmann statistics. Today our aim is to find the most probable distribution in each case, that is in all the three cases, consistent with the macro state. How we do it? We maximize the expression for the number of microstates corresponding to a valid distribution. That is, we have to maximize the expression for T and I consistent with the macro state which we are talking about. Once we do that, we will get the most probable distribution. That most probable distribution represents the thermal equilibrium distribution. We have to do it for all the three cases. That is the Fermi-Dirac case, Bose-Einstein case, and Maxwell-Boltzmann case. We will be doing the same procedure as we have discussed in the classroom. We derived the Boltzmann distribution for thermal equilibrium situation of an assembly of particles which were distinguishable. They were distinguishable due to their localization, right? So the procedure will be same. So let us first discuss the Fermi-Dirac statistics. So first situation is our Fermi-Dirac statistics. Now what we do, we need to here maximize TFD, the expression which we have discussed in the last lecture, or we can maximize conveniently its logarithm. Ln TFD subject to the usual macro state conditions. What are the usual macro state conditions? That summation I small ni is equal to capital N. I name it first. Capital N is the total number of particles in the system, and that is fixed. Similarly, we have total energy of the system, which we can write summation I ni epsilon I, which is equal to U, which is the total energy of the system, which is also fixed. So we have to maximize ln TFD subject to the macro state conditions, that the number of particles in the system capital N is fixed and the total energy of the system U given by equation 2 is fixed. As I told you, we have done it for the localized particle case. So what we do, the method is simple. We simplify the expression for ln T using Stirling's approximation, and then find the conditional maximum using the Lagrange method. So let us do it. So for Fermi-Dirac statistics, in the last lecture, we have already derived the expression for the number of microstates, that is TFD of Ni, that is corresponding to a valid distribution, is product over all I groups Gi factorial over Ni factorial times Gi minus Ni factorial. So this is the expression we discussed in the last lecture, valid for Fermi-Dirac statistics, that is the fermions, Gi factorial over Ni factorial times Gi minus Ni factorial. What we do, we take the logarithm. Let me use another color. Taking logarithms of this equation, of equation, we get I will change the color. We get ln T FD is equal to summation I ln Gi factorial minus ln ni factorial minus ln gi minus ni factorial, right? Let me write here square bracket, because summation I is for the whole expression. So it is summation I ln gi factorial minus ln ni factorial minus ln of gi minus ni factorial. So you can see the product in the above equation becomes the sum, which is the property of logarithm that you can understand. Now I can make use of the Stirling's approximation. So let me do. So it is equal to summation I gi ln gi minus ni ln ni minus gi minus ni ln gi minus ni. Summation is for whole expression. Let me check it. Gi ln gi minus ni ln ni minus gi minus ni times ln gi minus ni. So we have used Stirling's approximation. Let me write it here. Using Stirling's approximation, which we have already discussed in the previous lectures, right? So check this at home. This is your assignment. Check this at home. Then what we do? Then we use the Lagrange method using the Lagrange method for the maximum condition, for the maximum condition, we write d of ln t, d is the differential, plus alpha dn plus beta du is equal to 0. I name this third. D ln t plus alpha times dn plus beta times du is equal to 0. Now, how it comes about, as I told you, we have done it, discussed it, explained it for the localized particle case in the classroom. So you can go through that and understand it. Here I will write it directly. Now what we have to do, we have to substitute. Substituting ln t, our ln t is ln tft from above together with equation 1 and equation 2 for n and u gives after differentiation. That is, in the 3 we have to substitute, and instead of ln t we have to write ln ft given by this expression. Then we have to use our equation 1 and 2 for n and u and differentiate. When we do it, we will get this. Summation I ln of gi minus ni over ni plus alpha plus beta epsilon I whole times dni equal to 0. Let me check it. Summation I of ln of gi minus ni over ni, then plus alpha plus beta epsilon I whole times dni is equal to 0. As I told you, you need to check it at home. You simply use the Lagrange method for the maxima. We're actually maximizing what? We're maximizing ln tft under the restrictions imposed by equation 1 and equation 2. Now this Lagrange method enables us to remove the summation sign for the specific values of the multipliers alpha and beta to obtain for the most probable distribution ln of gi minus ni. Now this is ni star. This is the most probable distribution. We know the most probable distribution represents the thermal equilibrium situation. So it is now ni star plus alpha plus beta epsilon I is equal to 0. Right? Rearranging this expression, rearranging this expression, we get Ni star, the most probable distribution, is equal to Gi over exponential of minus alpha minus beta epsilon I plus 1. Plus 1 is outside the exponential. Gi over exponential of minus alpha minus beta epsilon I plus 1. Now, we can write the expression for Fi, which we called the filling factor in the last lecture, or the equilibrium occupation per state. So let me write, therefore, Fi is Ni star by Gi, which is simply 1 over exponential of minus alpha minus beta epsilon I plus 1. Let me name it equation 4. This is my equation 4, right? 1 by exponential of minus alpha minus beta epsilon I plus 1. You can see that this Fi, which is now the equilibrium occupation per state, that is the occupation per state in thermal equilibrium situation, because it is Ni star, that is the most probable distribution. So this Fi, as you can see, is independent of Gi. That means the grouping of the states has no influence, explicit influence on the equilibrium occupation per state Fi. And you can see this distribution function contains no details about the states except their energies. Hence, equation 4 can be written this way. So, equation 4 can be written as, we write it, FD function of epsilon, because it is dependent on the energy, is equal to 1 over exponential of minus alpha minus beta. Now I will write epsilon, not epsilon I, plus 1. I name this equation 5. Let me encircle it. So this is our first case. We have found the filling factor pertaining to the Fermi-Dirac case, which is simply what? It is the equilibrium occupation per state for fermions at thermal equilibrium, as I told you. It's 1 by exponential of minus alpha minus beta epsilon plus 1. So next thing we have to discuss now the Bose-Einstein statistics. This was Fermi-Dirac. So we have to follow similar steps. So my second is now the Bose-Einstein statistics. So second one is Bose-Einstein statistics. So let me write in this color. As I told you, derivation of the Bose-Einstein distribution follows the analogous steps. So let us do. What is our expression for TBE for a valid distribution? We have found that in the last lecture. So let me write. It is the product for all I groups. Then in the numerator I have Ni plus Gi factorial. Then in the denominator I have Ni factorial times Gi factorial. Let me check it. Bose-Einstein TBE of the valid distribution Ni is product over all I groups, all groups I, Ni plus Gi whole factorial over Ni factorial Gi factorial. So let us proceed. Taking logarithm and using Stirling's approximation, taking logarithms of this equation, that is TBE equation, this equation of this equation, and using Stirling's approximation, we get. So what we get, I will change color here. We get ln TBE is equal to summation I. Again, the product is converted to summation by the application of log Ni plus Gi times ln Ni plus Gi minus Ni ln Ni minus Gi ln Gi. This is G here, ln Gi. Summation is for whole expression. Let me check it. Summation I Ni plus Gi times ln Ni plus Gi minus Ni ln Ni minus Gi ln Gi. Again, you have here also the home assignment. Let me mention it here. Check this. And what we have to do, as we did in the last case, that is the Fermi-Dirac case, substituting this into equation 3 together with the restrictions equations 1 and 2. Let me adjust my pen. Equations 1 and 2, we get what we have to do. We have to substitute this expression for ln dBE in equation 3 and use the restrictions imposed by equations 1 and 2. This is our equation 3. This one, d ln t plus alpha dn plus beta du is equal to 0. And we have to make use of the restrictions on the number of particles and total energy expressed by equations 1 and 2. So let us move. When we do this, we substitute it, we get summation I of ln of Ni plus Gi over Ni, then plus alpha plus beta epsilon I whole times dni is equal to 0. You have to check it. Summation I ln of Ni plus Gi over Ni plus alpha plus beta epsilon I whole times dni is equal to 0. Then the form of the equilibrium distribution is again obtained by setting each term of the sum equal to 0. Let me write. Therefore, ln of Ni, now I will write star because it is now the most probable distribution representing the thermal equilibrium situation, plus Gi by Ni star plus alpha plus beta epsilon I is equal to 0. Ln of Ni star plus Gi over Ni star plus alpha plus beta epsilon I is equal to 0. After rearranging, we get after rearranging, we get this Ni star is equal to Gi over exponential of minus alpha minus beta epsilon I minus 1. minus 1 is outside the exponential. Gi by exponential of minus alpha minus beta epsilon I minus 1, or in terms of the distribution function, which is ultimately the equilibrium occupation per state, Fi, I can write Fi is equal to Ni star over Gi, which is equal to 1 by exponential of minus alpha minus beta epsilon I minus 1, right? Exponential of minus alpha minus beta epsilon I minus 1 is outside the exponential, or we can write F as function of energy. So I can write, first let me name this equation. This is my equation 6. So let me write this way now, or F BE Bose-Einstein function of epsilon is equal to 1 over exponential of minus alpha minus beta epsilon. Outside the exponential we have minus 1. This is my equation 7. So we have, this was my 5. Okay, so we have found the filling factor or average occupation per state at thermal equilibrium situation for bosons given by equation 7. So let us consider now the Maxwell-Boltzmann statistics, which is the third case. So the third case is Maxwell-Boltzmann statistics. So we know this is valid for dilute fermion or boson gas, and we also know that by dilute we mean Ni is much less than Gi for all I. That is, all energy states in all groups are sparsely occupied. So let us find the distribution function. Our TMB is product over I Gi raised for Ni over Ni factorial, right? So applying logarithm, applying logarithms to this equation, we get ln TMB Maxwell-Boltzmann is equal summation I, and I have Ni ln Gi minus Ni ln Ni plus Ni. Ni ln Gi minus Ni ln Ni plus Ni. We have also used here Stirling's approximation. Let me write it using Stirling's approximation. You need to check it. Check it. Again, product is change it into sum by the application of logarithm. What is the next step? Using equations 3 with 2 and 1, using equations 3 with equation 2 and equation 1, that we have to put this expression for ln TMB in 3, then make use of 1 and 2. So using equations 3 with equations 2 and 1, we get so what we get? We get summation I of ln of Gi by Ni plus alpha plus beta epsilon I whole times dni is equal to 0. Let me check it. Ln Gi by Ni plus alpha plus beta epsilon I times dni. Again, you have to check it. Now again, removing the summation for the equilibrium distribution and rearranging, we get Ni star is equal to Gi times exponential of alpha plus beta epsilon I. Gi exponential of alpha plus beta epsilon I, and I star represents the most probable distribution, which represents the thermal equilibrium situation. So again, now we can write the corresponding filling factor. Average occupation per state at thermal equilibrium pertaining to Maxwell-Boltzmann statistics. So let me write, therefore Fi is equal to, let me get my pen back. Fi is equal to Ni star by Gi, which is simply exponential of alpha plus beta epsilon I. Exponential of alpha plus beta epsilon I. Let me name it equation 8, or I can write it as distribution function. I label it FMB of epsilon is equal to exponential of alpha plus beta epsilon. This is the equation 9. Let me write here this neatly. This is here is equal to fmb of epsilon is equal to exponential of alpha plus beta epsilon. So this is the third case. This is the average occupation per state at thermal equilibrium pertaining to dilute gas. There is a Maxwell-Boltzmann statistics case. You can note that this distribution function, equation 9, has a similarity to the Boltzmann distribution which we found for localized particles in the previous lectures. So we have completed today's lecture. Let me summarize before leaving. So our aim was to find the three equilibrium distribution functions. First for Fermi-Dirac case, that is our this equation 5. Then we discussed Bose-Einstein statistics. So we got this as our result. Let me encircle it. Then we did the same for the Maxwell-Boltzmann case, that is equation 9. Let me encircle it. So this is all for today. Don't waste your time. Go through all the lectures. And don't forget to like, share, and subscribe my channel. You can give comment. You can comment. You can have any query. You can comment in the comment box. I will try to look into those queries. Thank you. Assalamu alaikum.